Hi everyone. On this video, based on the third node of from the basic to graduate mathematics, we will explain relations, equivalence relations, equivalent classes, and partitions. In the previous two nodes, we studied set functions, images, inverse images, one-to-one functions, inverse functions and composition functions and its characterization of one-to-oneness and onto-ness. The note today is the natural next step. A function was a special kind of so-called a relation that assigned exactly one output to each input. This note, we begin with more general concept of so-called a relation. And then among other relations, we study a very special kind of relations called an equivalence relation, which groups objects into the same kind. These notes organize into few major stages. In the first stage, we look at function again as a special case of relation. A function connects elements of two sets by ordered pairs, but it satisfies the special condition that each input is connected to exactly one output. And in this another next stage, we define general relation. A relation is a way of recording which element is connected to which element between two sets. Especially, we define an equivalent relation among relations on one set. An equivalence relation is a relation satisfying reflexivity, symmetry, and transitivity. In another stage, we study examples of equivalence relations. These include sharing same sets, grouping integers, and so on. And from there, we get the idea of defining the concept of the partition. A partition divides one set into several pieces that do not overlap while still covering the entire set. And in the final stage, we reached the key conclusion. Equivalence relations and partitions contain the same information. If we have an equivalence relation, its equivalent classes partition the set. Conversely, if we have a partition, we can define an equivalent relation by saying that two elements when are related when they belong to the same piece. The core message of this note is also very, very important. In mathematics, we often do not look at objects one by one in isolation. Instead, we often treat different objects as the same according to some criterion. For example, we may divide integers into even and odd numbers. We may group geometric figures according to congruence. Congruence. We may treat vectors as the same if they differ by an element of certain subspaces. The starting point of these ideas is the concept of equivalent relation. Equivalence relation. So let us begin with the concept of relation. Previously, we learned about functions. A function was a rule that assigns to each element of one set exactly one element of another set. But we can look at a function from a slightly different viewpoint. A function is a collection of input-output pairs. From this viewpoint, a function is a relation between two sets, but it is a very special kind of relation. Every input must be connected to one output. and one input must not be connected to two or more outputs. In other words, a function is a relation satisfying existence and uniqueness of function values, whereas a general relation does not satisfy such a strict rules. An input may be connected to no output. An input may be connected to several outputs as well. A relation is simply a structure that records which element is connected to which element. For example, consider the set A and B this way, then we can simply just define the relation in this product set by just picking these two elements. Then we can simply regard one is related to by 4, 2 is related by 4 from this relation. So there are tons of ways to define a relation, and the function is special kind of relation. And one of the special kind of relation that we are using most is so-called equivalence relation. An equivalent relation is a relation defined on the product of A cross A, not A cross B in general. So it's a relation used to group objects into the same kind. For a relation to be an equivalent relation, it must satisfy these three conditions. First, every object must be related to itself. This is called reflexivity. Second, if one object is related to another object and the other object is also, and then other object must be also related to the first object. This is called symmetry. Third, if the first object is related to the second object and the second object is related by the third object, this is called and then first object should be related by the third object. This is called transitivity. Why do we need these three conditions? An equivalent relation abstracts the idea of treating objects as the same. But for the word of same to behave properly, we need these three conditions. First, reflexivity says an object must be the same kind as itself. If an object is not even the same kind of itself, then the phrase same kind does not work properly. Second, symmetry means that the relation has no direction. If I'm the same class as another person, then that student is a person is also in the same class as me. If I have the same reminder as another number, then that number also has the same reminder as me. Equivalent relation is not one directional relation, it is a relation of mutual sameness. Third, transitivity means that sameness must continue consistently through a chain. If I'm the same class as the second person and the second person is in the same class as the third person, and I'm also in the same class as the third person. Without this condition, the idea of one coherent group would collapse. Therefore, an equivalence relation is a relation that is related to itself, symmetric in both directions, and stable under chains of relations. When these three conditions come together, one set can be divided into several meaningful groups. Now let's look at the example. So for example, if we even collect the functions from x to y, which are all bijective, then you can show that such a relation becomes equivalent relation because the identity function is the case to make the reflexivity, and the symmetry is coming from the inverse function, and the transitivity is also follows from the second note that you show the characterization of the one-to-oneness and the onto-ness. And there are also few other kinds of examples to investigate the properties of the one-to-oneness and onto-ness, but those are also extremely useful. So we will also now move on to the concept of the partition. A partition divides one set into several pieces, but we cannot divide it arbitrarily. For a division to be a partition, we require these three conditions. First, each piece must be non-empty. Second, different pieces must not overlap. Third, when all pieces put together, they must recover the whole original set. So a partition is a way of dividing a set without missing anything and without overlapping pieces. Intuitively, we can partition people by departments, we can partition integers by remainders, we can partition geometric figures by congruence classes, and so on. We can talk about so many applications of the equivalent partitions, and what we really care is, in fact, they are related by describing either the equivalent relation or the partition, because it turns out that they are actually the same. So if we have the equivalent, like the relation, so suppose if we have our equivalent relation, then we can choose one element, say X, then equivalent class that of that element is the collection of all elements equivalent to it. In other words, it is the group collection or objects of the same kind as that element. And you can show that the collection of equivalent classes becomes a partition. And thinking about the meaning of why this must be the case, well, it's very important to look at concrete examples to think about why this is supernatural with concrete examples. And moreover, equivalent relation partition are not just a one side, one direction implication, but one-to-one correspondence. Now, if we have an equivalent relation, then we can define the relation by assigning the relation that whether or not two elements belongs to the same piece. Then one can show this becomes the equivalent relation. And moreover, if one go from one to the other, then you can also recover the exactly same information. By all means, the composition of these two will be the identity. This conclusion is super powerful because an equivalent relation is a logical criterion for deciding what should be treated as the same. A partition is the actual collection of groups produced by that criterion. So then equivalent relation is a rule, a partition is the result produced by the rule. So we now know, mathematically speaking, they are actually exactly the same, so that we are treating the same abstraction via the two different like the angles. One is based on the relation, the other is coming from the partition. So this note may look elementary set theory, but reality, it is the first starting point of modern mathematical ideas, identifying, gluing, classifying, and taking quotient. And the core sentence of this note is this: an equivalent relation is a rule that decides which object should be treated as the same. I do not know which demonstrate this properly. I think could be good to just look at the definition of equivalent class. I thought I already pointed out somewhere here, but I cannot find it. Well, this is one kind of example, but I wanna just point it out the more general one. So we define the relation here, and where were we? Should be somewhere here. Here we go. So from here we can consider the concept of the quotient set, which is crucial concept of algebra, topology, and geometry. An equivalent relation is a rule that decides which object should be treated as the same. A partition is the collection of groups actually produced by that rule, and equivalent relations and partition explain each other completely. That's it for the third note of the basic set theory, and we will move on to the introduction to real analysis from the fourth lecture note. Thank you very much for watching this video. I will see you next time.